All right. How you doing, guys? How you doing? We'll start now. We are GAME2005, Game Physics, and this is Lesson 1. My name is Tom. I'll be your instructor for this semester. I am recording this live on YouTube, so if you don't like it, you can go, right? You have the wrong class? Okay, you can go. But if you don't mind, I'm going to be recording me. I'll be recording my screen. I won't be recording you guys unless you talk and you ask a question, then your voice may come up. I do have a lot of videos. This is me. I've been teaching since 2011. I have a background in software engineering and game development. Recently, my team won the Technical Innovation Award at Level Up in Toronto in April. We built a OpenGL game, which is pretty cool. I have 1,477 videos on YouTube. I record all my classes, so this is a good thing for you guys. And it's a really good thing for this course because this course is not typically an easy course. Only because there's math, and people just hate math, right? So I'm so sorry. If you hate math, we're going to get you through it, right? It's a necessary evil if you're a game dev, right, person. If you don't like math and you're a game dev person, I don't know how you're going to make it through. It's pretty tough. I also got a playlist for this course, and if you want to go to that link, you can actually download the playlist. Some of these I already have this course. I've done it before, and this course has a bunch of videos already, so you can always look ahead to see what I'm going to be talking about. I'm going to be re-recording some of them, only because there are certain changes I have to make. Because last time I did this course, we had a strike, right? So some of the course was incomplete in parts. I rushed through some of it because we had almost like a compressed schedule the last time we did it. So I may have to re-record the stuff, and this is the link, if you guys can see that, for you to get it. Now, I have to wait a day or so. We're cross-listing the course, which is going to happen probably tomorrow. So everyone will be on the same schedule. So I haven't posted these slides yet, but I will post them all. And you'll have a chance to kind of look ahead and all that kind of stuff. All right, so things to note, I'm not a mathematician or a physicist. I'm a game programmer and software engineer. That's what I do. But I know how to do physics and math. So I don't have a PhD in math or physics, thank God. That's crazy stuff. I envy the people who can go through it. It's really, really tough. One thing I would like you guys to do for this semester is connect with me on Slack. I'm going to be using Slack for communications in terms of our announcements, things like homework help, all that kind of stuff. Please, I urge you to connect with me on Slack. I will be posting some stuff there. There will be a programming component to the course, which I'll go over in a bit, right? Because this is something we wanted to change. That's Philip and Alex and I, right? So we're looking to add that component in this semester. It's the first time. You'll probably be using SDL, which is something you're probably going to be learning at the same time this semester. So that's why I recommend highly that you connect with me on Slack today. Do it today. Don't wait, because there's going to be a chance for us to answer some questions and all that kind of stuff. All right, course info. Let's go over this a little bit. This is slightly different than what it says on the outline. So let's go over what we're going to be doing for this course. Again, I'll try and get the outline changed officially this semester. So again, we're sitting in the first week of class, introductions, all that kind of stuff. We're going to be talking about geometry and trig this week. And you might say, well, why do I need geometry and trig? You need it. If you don't remember geometry and trig, then physics will be quite a chore for you, right? You need to know triangles. You need to know how to do triangles. So I'll do a bit of a review this week. So it'll soften you into the math and a little bit of algebra, all that kind of stuff. And that'll be this week. What I've done is I've broken this physics class down into 3 modules. So you'll have the first module, which is math, calculus, like that kind of stuff, right? Then we'll go into the physics part, which is 4 weeks, right? So from week 4 to week 9 or 10. And then we'll get into test number 2. And test 2 will be the physics piece, right? So you'll be tested on each piece, and they won't be mashed together, right? So whatever I talk about first, you'll do that test. And then we'll talk about a new subject. You'll do that test, and those will be done, right? And then we'll do the last part, which is the most exciting part, which is, and the most difficult part, which is this piece, oops, down here, which is all about collisions in 2D and 3D, right? The reason why I'm saying this part's the most dangerous and crazy part is because there's programming involved, right? And if I'm giving some time for you guys to get to the programming piece, because I know you're supposed to be learning STL this semester, yeah? I think. So if that's true, then hopefully it'll give you some time to pick some of that stuff up, and then we'll get into this last piece here. This is the trickiest part because, just a second, because there's gonna be some code examples, and your assignments will be a programming assignment. Okay, so there'll be a programming assignment in the second half or of semester, and that's why it's the most difficult part. Yes.
Just checking the standard template library.
Yes.
Okay.
Yeah. Don't worry, I won't make you write.
I wasn't sure if you said STL or SQL.
SDL. SDL.
Yeah. Okay.
Yeah. SD.
Oh wait, SD.
SDL.
Oh,
SDL.
ST.
No.
Oh, okay. So
no, I'm not going to make you write the standard template library again. No, that would be bad. And I'm not going to get you to learn it. You should. It's going to be part of it. I don't think Alex or Philip are going to make you not do it. Although some people are against using STL because it's not.
Boost for everything?
Well, no, not boost, not even boost. They just think it's inefficient. They write their own, right?
Yeah.
I don't recommend it though. I highly don't recommend not using the standard template library in the beginning when you're learning C++ and all that kind of stuff. Anyway, so that's really the high-level plan. Again, I will share this with you, but if you can tell, the first part, let's go back up to the top. The first part is trig calculus. I need a couple weeks for calculus for derivatives and integrals. And you might say, well, am I ever going to use calculus when I do game dev? And chances are you won't. Just being honest. Like I've never had to do it. I can program a lot of that, my physics world on my own. But sometimes what happens is, we want to, derive some kind of formula or whatever. And it's good to have that background to understand how to check your work and all that kind of stuff. Some of you may never build a physics engine. You might probably use it. And chances are you will. You'll probably use somebody else's physics engine because it's already been tested and optimized. And that's fine. But if you wanted to do your faux physics or have some kind of if you're going to do a platformer or something like that, or even just collisions, then understanding calculus and all that kind of stuff is pretty cool. So the first test is week 5, right? Like I said, and it'll be all on trig, derivatives, and integration. Okay, so that's when the first test is going to happen. We're not going to do the test in this room. We're going to do the test in lab. Okay, so that's the mode of the test. So when we get together, I think all of your labs are in C401, if I'm not wrong, or maybe one is in C235. I don't know, or 435. Anyways, so there is one of the labs I think is slightly different, but I think most of them are in C401. You'll be doing it in there. You'll need a computer. I'll allow you to to use your laptops if you have a laptop and all that kind of stuff. It'll be a Blackboard test most likely, and there'll be true, false, multiple choice kind of questions. You'll be given some time. You'll also be allowed a cheat sheet. I'm just telling you this in advance. And usually cheat sheets are not good, guys, because that means that you don't have to remember formulas. I'm just going to get you to figure things out, which is more difficult, right? So there won't be any formula memorization in this course. I won't get you to do that, all right? On the downside, you need to know what you're doing, right? So you won't get marks for understanding or remembering the formula at all. So that's happening, again, first test, so test 1. You have quite a few weeks to study. And like I said, you've got all the videos ahead of time if you sign up to the YouTube channel to watch. So you can kind of watch ahead. I'll also be posting all the slides as soon as I get access to Blackboard with the cross-listing. So you have all that stuff. I'll post all the slides up for you guys ahead of time so you guys can go through it and get a kind of a lead on what's happening. Any questions for the first part? So this is calculus and trig, first part. Not the most exciting part, and this is the part people have trouble with, right? Because they're like, I hate math. Or I really don't like, calculus or whatever, but I love math. Assignment 1, that's also going to happen. Next week, I'm going to give you your assignment number 1, right? I may post it a little early to give you guys a jump on it if you're interested. I highly recommend for success, you start your assignment as soon as I give it to you, okay? It takes a little bit of time to figure out, and people hate math assignments, right? So I'm just being honest, right? Telling you the truth. I've done this a few times. So that's the thing. Assignments will be done in groups. Okay, so that means you can do it with somebody else. Yes. I don't know, maybe 2 or 3. We'll talk about it next week, right? And some people say, I don't want to be in a group. I hate groups. I hate my partners. They all suck, right? I don't know. I'm just saying. Some people say that kind of stuff, right? No one works. I only work. I'm the only worker, right? Everyone else is a slacker. Just me. I'm the only worker, right? And if that's true, guys, right? Well, you guys are in big trouble because that means all of you are slackers, really, if you think about that, right? If everyone's a slacker except for me, right? Well, then everyone's a slacker. But I don't believe that. I think that you can find somebody that you've worked with before that works. Find at least one other person. And if you have trouble finding a partner, I will assign one for you, right? Don't make this a task, a chore. But I really do recommend that you work together in pairs, at least, to do your assignments because it'll make it easier for you. Easier for understanding. You can, it's almost like a homework group, kind of work together with the other person to understand some of this stuff. And then when it comes to tests, you're going to be better, right? One of the things I always say for success in this course, attend class. I know this, you've heard of this before, but I'm going to say it anyway, right? Attend class, make sure if you don't understand something, watch the videos again. I'm going to go over the same detail in the videos that I'm talking in class. Anyway, there is no textbook in this class only because it's kind of a mishmash of different things. We've got some calculus and trig, we've got some physics, mostly kinematics, all right? So like, motion. And then there's the collisions piece. And I'll be talking about which book I'm going to be using throughout. There's different books I'm dragging information from to put this thing together. But there is no one textbook to buy. So use this. If I talk about it, this is the rule that I'm going to tell you about. If I talk about it in class and I talk about it in lab, it's fair game for the test, okay? If I don't talk about it in class or in lab, I'm not going to put it on the test, okay? Just to be fair, right? Because some of you may not have access to resources as much as others. Okay, so that's really the how for assignment number 1. You guys will be getting together in pairs. It'll be short. There probably won't be any programming component to the math part. Okay, I'm just letting you know. And also because you're still learning the STL library, I'll probably share that with you anyway. I probably will give you a template next week if you want to start going and practicing. But that stuff is the first part is all kind of a math thing. And then when we get into the physics part, we're going to be talking about motion, simple motion, motion in 1 and 2D, and then the laws of motion, so that's Newton's laws, right? Some of you may have done high school physics, and it'll be a review for you. I'll go over that again. One thing I'm going to try and drag in as much as I can is vectors, right? Because, vectors and matrices probably are the 2 most important things you need in game dev, especially if you're doing things with OpenGL or DirectX or whatever it's going to be. So we have to kind of go over those concepts one more time with you guys. You guys should have already taken that, if I'm not, last semester, yeah? So it'll be a bit of a review. And how do we apply those same concepts to physics, right? How do I, instead of having a simple equation, we're going to try and use vectors as much as possible. And again, I'll be talking about where I'm getting that stuff as we go forward. Okay, so that's the physics piece. The most interesting part to me, again, like I said earlier, is the collisions piece. You need to know collisions in order for you to have a real game, right? Some of you already kind of figured it out. The simplest form of collision is distance, right? Or a capsule, right? Some kind of way of intersecting between a capsule and a plane, a capsule and some kind of cube, some kind of bounding box anyway that you put around your object, right? And then that way you kind of have a collision. You can detect collisions, and without collisions, most games aren't games, right? They're whether it's 2D or 3D, you need to know collisions, and they help you do things like score or achieve or whatever. And then we have to talk about collision response. So there's collision detection. Okay, I got hit, and then collision response. Okay, now what happens, right? So do I bounce back? Do I fall? What happens? Do I just disintegrate? So that's like collisions. And then even though it says there's 3 weeks for collisions, I might move one of the physics pieces together to give you an extra week. Yeah.
So just since you said we'd be using STL, I'm guessing this course is in C++?
Yes.
Okay.
Yeah, we won't be using JavaScript or Python or something else, right? And you guys are probably
finally out of JavaScript, all those nulls and undefined.
Well, Don't talk to me about it because I love JavaScript, but only because I program in TypeScript, so I'm pretty good with it. But yeah, we won't have to be doing JavaScript now. This will be real. Most companies don't hire you for JavaScript, your JavaScript skills. If you're a game dev, right? They want your C++ skills. So yeah, so that's something that we'll be talking about more. Collisions, and again, if I can try and get some programming practice in for the physics part, I'd like to do that too, because to try and do some kind of particles, like show particles that move around the screen, that kind of thing. That's what we'll be doing on the physics piece, right? So that's really the schedule in a nutshell. Again, I'll be posting these slides. You'll have this schedule. Please use this as your Bible, right? So if it says there's going to be an assignment, it's going to be an assignment. Typically in the past, I've had lots of quizzes and that kind of thing, but I find it's really overwhelming for some people to have like a quiz every single semester, every single lecture. However, I'm not going to discount them. There might be a chance I'll see how you guys are doing, and if you guys are doing well, then I'll probably post a quiz to help you with your test. Usually a week before. I'm not going to put it here because it's going to be bonus. So if you fail your quiz, who cares, right? But I'll probably add it in as a bonus option. So if you do your quiz, if you're here, and it'll probably be an online quiz. So please bring your laptops. Or what I might do is I'll put it in the labs. So even if you don't have a laptop, you can do it, right? You'll probably have some time to do it that day. If I do post quiz. Okay, so that's it. Week 8 will be the semester break this semester. That's October 22nd to October 26th. There'll be no classes during that time. But you'll be getting assignment 2 around just before the mid-semester break. Assignment 2 is more difficult because it's physics, right? So there'll be some physics questions that I'm going to ask you and your partners to do. So again, just like I said with assignment 1, get a jump start on it. Don't wait. I won't be giving extensions, so don't ask me for extensions because you guys are going to have a tight schedule. If I extend one of these assignments because they're a little bigger, it'll really affect you negatively, not positively. And then, of course, assignment 3 is the biggest one. So if you notice, it builds. So assignment 1, you have like a couple weeks to do it. Assignment 2, you have like 3 weeks, 4 weeks to do it. And assignment 3, you have like pretty much half of the second half of the semester to do it, right? Because there's more stuff. There's programming. There's a little bit of graphics. There's some other stuff that you have to do. So assignment 3 is more difficult. Now, to balance that, what we've done is we've kind of have a split like this. And I've kind of made this really big so you guys can see it. So assignment 1 is 15%. Again, let's do week 4. Test 1, again, 15%. Those first 2 things, because they're math, try and make it a little easier. I try to weighted them a little bit less than I could have. I was thinking of making it 10%, but then some people are really great with math, so I don't want to take that away. But if you notice the second parts, assignment 2 and test 2 and assignment 3 and test 3 are worth more, right? So that way, if you're not great at math, even if you don't do great, it's not going to completely kill you in this course. Still worth 30%, okay? So that's really the breakdown of where the marks are coming from. Any questions around marks and the spread and the schedule? Yeah.
So if this is a lecture and we're just going to be talking about the general things, what are we doing in the labs then?
Work. I'll get you guys to practice. I'll give you some examples.
Okay.
We'll go through it. I'll ask you some questions. I may actually come up and try it. And we may do some quizzes or whatever it's going to be.
And,
highly recommend you go to lab. Right?
And labs are not recorded for you.
I will try and record the last lab. Normally I don't record them, but I will try and record the last lab. Typically I don't want to record them because I want you there, right? Only because it's good for you to go there and practice questions. It'll also be a chance for you to do your assignments, right? So it's assignment time where you can ask me for help, right? So you can say, I don't get this. Am I going down the wrong path? Can you help me out? And I think that might be a good opportunity for you guys, as opposed to me just like it just being a pure download for another 2 hours. I don't want that. I think it's better that you get help during that time. So that's what we'll be doing in labs mostly. Okay, so I'll be going through some example questions. I won't go over everything again, just the example questions that are kind of aligned with what I talked about in the lecture. Okay, any other question around structure? Please ask them now, because you're here with me now. You can ask me your questions. Okay, how about this? I'll ask you some questions. So who hates partners? Anybody hate partners? Yeah, there's people some hate partners. I know people hate partners. So again, if you guys really don't want to do with anybody else assignments, you could do it with yourself on your own. Did I say that wrong? Do it with yourself. Yeah, you could be on your own and stuff like that. That's totally fine. But I highly don't recommend it, right? It's like I said, there's just too much stuff. Sometimes you have so much work to do, and it's good to work with other people. How about this? How about who loves math? Anyone love math in the course? Oh, okay. I might have some pretty good results then. If you kind of like math, huh?
I love learning about theoretical math. I hate it when I actually have to do math on paper.
You hate it when you have to do math on paper. Well, sometimes, buddy, you have to do math on paper. I don't know what to tell you, right?
Or you know, like the paper.
I'll tell you this. When you guys learn how to do shaders, so if you guys have anyone ever do OpenGL or any kind of, some people may have already, that's good. So when you do OpenGL, right, the shader program is one big math equation, if you think about it, right? So if you don't know how to do shaders, and if you don't know how to do math, especially things like linear interpolation, all that kind of stuff, you're going to get yourself in trouble. I mean, it's part of what we do when we build the game, right? So it's always good when you have a group that, well, at least one person's really good at math, right? So they can figure some of this stuff out. All right, let's get to the heart of it. So we're talking about geometry and trig. And part of it, I'm just going to make this a little smaller. Part of it is, I want to talk about this so you guys know. So this is the lecture piece, guys. Okay, we got angles, triangles, and really that's it that I want to talk about. I don't want to talk about too much about trig, but really without triangles, figuring out physics is like really hard, right? You can still do it with other methodologies, right? Like using vectors and matrices and stuff. But triangles make things a lot easier. I found when I was doing physics, especially game physics, that knowledge of triangles and all that kind of stuff, just how they work, or just reminding myself from high school how trig works is really, really helpful. Everything from calculating distances to angling your deflector shields, I don't know, to whatever you're going to do in your game, calculating the next pixel that you're going to move your 2D or 3D piece to, aiming your guns, whatever you're going to do, it's all trig, right? And it has nothing to do with physics, but we use a lot of those things. So, so we talk about shapes. You can talk about primitives. A lot of times when you use commercial game engines like Unity or Unreal, we start with primitives, primitive shapes, cubes, planes, spheres, and some kind of triangular shape. Most objects are made with triangles in graphics. Again, I'm just high-level review, right? So when we do things in 2D or 3D, we have a polygon count, right? You guys should know this, yes? Hopefully, yes, you know it. Hey, someone knows it. All right. So yeah, so you have all these triangles. I'm just going to pull up some diagram here. So let's use Blender for now. You guys may or may never learn Blender in this part of your course, and that's perfectly fine. If my Blender would start, it would be nice too. Yay! And I'm really taxing my system. I'm presenting. I'm recording. Everything else I want. So you get like your kind of your 3D plane kind of thing, and hopefully you guys can see that. Maybe not. It's probably too bright. But anyways, the idea is that you have primitive shapes, and whether you have a bounding box that's in 2D or 3D, you have a polygon count. So when I have a thing like this, what I'm actually doing is when I want to kind of project this thing, I have a quad or several quads on the screen, and a quad is just basically two triangles. And in Blender, what you can do is I can, wow, it's really bad. I can split a quad by using into two triangles. I'm not sure if you can see that, but there it is. There's a cube, and it's split down into two triangles. Let's see if I can turn the lights off for you guys. So this concept stuff, okay? That's the wrong way. How's that? Is that better? All right. So you've got this cube, right, and it's split into these two triangles, right? So again, even though you may think, well, I'm never going to need trig. A lot of times, what we do with whether it's a cube or whatever it is we have triangles, whether we deform the triangle or not. So as an example, if I move the triangle up or whatever, it doesn't really matter. At the end of the day, you still have a bunch of triangles. And computer graphics, they likes triangles, right? It's how they're, kind of we create larger objects, more complex objects through a series of triangles. We can also use other shapes, right? But the triangle is, especially when it comes to displaying things on your screen with OpenGL, it's probably the easiest or smallest form that you want to use, right? So triangles is super, super important to understand. And triangles have some basic properties. Does anyone know some properties of triangles? This is important stuff. Yes?
They have 3 sides.
Yay, 3 sides. They have also 3 vertices, right?
Yeah.
3
We have
vertices.
3 angles.
We have 3 angles. What do the
They're only
angles?
counting interior angles.
Okay, the interior angles. What do the angles add up to?
180.
180. That's really important to know. 180 degrees, right? And there's certain identities we're going to be using to figure out these angles, right? To kind of figure out that if I know one angle, I can probably figure out the other 2, especially if one of the angles is 90 degrees, which you're going to get a lot of those, right? You're going to get a 90-degree angle and a couple of acute angles, and you're going to be able to figure out the other side, right? And there's some stuff. So some really cool stuff. In 3D and in 2D, it's not just vertices. What other things do you have in 2D and 3D, right? You have a couple of other properties of shapes like this. This is a primitive shape, right? So what other things do you have? You have edges, right? Those are edges. And you also have faces. So those are 3 things you're always going to have. Vertices, edges, and faces. This semester at another college, I'm teaching game assets, right? So there'll be a game assets course I'm doing for Blender later on this semester. I like to use Blender because it's very simple. It's open source. But if you like Maya or something like that, anyone use Maya or 3D Studio Max? That's good. Then you guys will be ahead because you kind of have the concept from a 3D perspective when we get to the second part of the course. But it's good to understand this stuff and to visualize, right? Because some of us are locked into math. Math is, for some people, it's not visual. They, they space out, which is, I apologize in advance because this is something we have to get through. So again, so triangles are basic units. Let me go back to this. All right. So again, angles we measure usually with degrees, but for most of the time, most computer applications require radians. Okay, so once we get into it, we're going to be talking about how to, a lot of times, convert degrees to radians or radians to degrees. Okay, we want to convert back and forth a lot of times. And why is that? It's just the way a lot of computer programs are made. They're a little quicker in terms of applications than degrees. So everything we pretty much use, we'll be using radians. And when we use radians, that means chances are there's 2 things. I can make it constant in my programming and make it so that it's a multiplier. So I take my degrees, multiply it by something, and then I get radians, right? That's kind of the easiest way to do it. And the other way back. But we're going to be talking about that. So here's, in this example, we've got a bunch of angles or basically some shapes that are inside of the circle. And a lot of times what we'll be doing is we have these marked radii, right? So A, B, and C in this particular case. And these arms that come out from the center of the circle, that's what they're called, radii, right? And they're all equidistant, right? Because it's a circle. It's a special kind of ellipse, right? That's perfectly shaped, right? So that's really the kind of circle. Another primitive that we're going to be using a lot, especially when it comes to collisions. So why is that? Because it's so simple. If I take a circle and kind of surround my object, a lot of times I can figure out the distance between the 2 centers of the circle to get a collision. I can kind of detect if an object is colliding with another object. All right, so that's kind of another primitive that we're going to be using. Okay, I'm not going to read all this stuff, but you can see that all the angles in a circle altogether must add up to 360 degrees, right? So really high level, easy stuff to remember, right? And you might get sidetracked and forget about that, but it's really important to understand that because when it comes to angles, it's kind of the main thing when to calculating things like force and friction for physics. Okay, so that's how angles work. Right angle is a special angle, and we're going to see a lot of that, a lot of right angles in our work. Because if I'm sitting in a particular place and we have a pixel grid, whether it's 2D or 3D, right? I'm sitting in a position and I want to calculate the angle between me, my player, and an enemy ship, right, as a good example, I'm probably going to have a right angle that I'm going to be using. And right angles are very helpful because there's a lot of things we can do with them, especially use things like the Pythagorean theorem, right, which is going to be your bread and butter, guys and girls, right? I mean, if you don't know Pythagorean theorem, that would be a bad thing when it comes to calculating distance. However, what's bad about the Pythagorean theorem? Anybody know? And please forgive me if I've covered this and if you know this stuff. I don't mean to ask you questions. Yes, thank you. Right triangle. What other things? That's a dependency for the Pythagorean theorem to work, right? If you don't have a right triangle, a right angle triangle like this with a 90-degree angle, you can't use Pythagorean theorem. You have to use something else. What else? I got two angles. I need two angles. Two sides for sure. Two sides. I need two sides. And in most games, we're going to have that. We're going to have kind of like an X and a Y coordinate. At the very least, you're going to, have those two parts, and you're going to be fine. What else? What's a bad thing about Pythagorean theorem or distance formula, right? What is a really, really bad thing? Think about every frame. You're doing something every frame. What am I doing every frame that's really bad with Pythagorean theorem? Anybody know? Square root, and that sucks, right? Square root calculations every frame. It's probably the worst thing you can do for your calculations, right? So there's other collision methods we're going to be talking about later on in this course. We're going to go from a broad phase type of collision to a narrow phase collision. There's different methodologies where you can use things like a grid. You know, if the person's inside the same grid space as you are, there probably is going to be a collision. But if they're really, really far away, do I have to check that every frame? Probably not. However, here's a bad thing. Imagine if from a performance perspective, you don't check until people get closer and closer to you. Then you can see like things slow down, right? Because you're checking a lot more because they're really close to you. And then you don't check at all when things are really far away. So you have inconsistent gameplay, which is also very bad. So you have to kind of balance that. And that's one of the decisions you're going to have to make, whoever your game engine programmer is going to be, or your gameplay programmer. You might have two people like that in your group when you program things from scratch. So yeah, so you've got this right angle triangle, which is kind of a really cool property of triangles. We can use that to calculate stuff. From a quadrants, sometimes we want to talk about quadrants. Two things to note about this stuff is the top right part of the quadrant, X and Y is both positive. Top left, or sorry, bottom left is X and Y are both negative, right? Typically in computer games, we use east, believe it or not. So this part over here, hopefully you guys can see this part over here, the easterly direction as 0, okay? Which way do I turn in most, computer graphics systems? If I'm going to turn, I'm going to say a positive number. Do I turn to the right or do I turn to the left? What do you think? I turn up. That's left, right? So I go counterclockwise a lot of times, right? Which is counterintuitive to most people. They're like, wait, why am I going left? Because positive y in a 2D plane is up, right? You think to yourself, but actually positive y is down because you start drawing from the top left most likely, right? In the coordinate space, usually top left corner is 0, 0, right? So that means I kind of start drawing pixels across to the right, like the right, and then down, right? To the right is positive, x positive. Down is also positive for y. And you're like, wait a minute, that means like if I go up, y is negative. And that can cause some differences in calculation when it comes to understanding how to turn and rotate, because when I turn up, I go to the left. When I go from 0, which is this part, so this will be east, and up here will be north, right? And I turn towards the north, right? And I keep turning in that direction until I have 360 degrees. So it's kind of a weird thing when you find you're rotating in space in 2D or 3D. And depending on your axis, so going back to Blender for a second, here's Blender, right? In this case, you might see the little arms, right? Are here. You've got your, your blue arm that's up, and you've got your red arm and your green arm, right? Well, these manipulator arms, right, represent axes, right? So your red is X, and this is standard across most graphics, 3D graphics manipulation programs, right? Your red is X, your green is Y, and your blue is Z, right? However, the orientation of this might be totally different than what you're doing in Unity or Unreal. Up is Y in Unity, right? Which is not the same here, right? So it depends on your coordinate space and the way your grid is laid out in your code. So that may affect your calculations. So again, going back to this, yes, I'm saying to you, most likely you're going to do a left turn when you're going to go positive, but there might be cases, depending on your coordinate space, where you do a right turn. Okay. Again, smaller angles, this review, acute, larger angles, greater than 90 degrees, obtuse, right? I'm going to talk about that kind of stuff a lot because, you know, you should kind of know the vocabulary, if you will. I'm going to be asking you some questions, and if you don't know what acute and obtuse angles, that would be very bad. Pi is a Greek letter that all of you guys should be very familiar with, right? Who knows how to say pi in like 10, you know, going down to 10 precision?
1, 4, 1, 5, 9,
Keep going.
6, 6, 5.
If you're a computer geek, then you should know as much as this guy, right? Sorry, I don't know. Yeah, I agree with you, man. That's that you should know. And the reason why is don't think about 3.14. More precision for pi means better accuracy when it comes to calculating angles in math. Luckily, most math libraries have pi, but you really want to use a math library in C++ to calculate pi for you. And probably not is the answer. So you probably want to use that as a constant in your code. That means one less thing to kind of pull into your code from a math library, whether it's STL or something else. Yes?
On the other hand, if you have a function which calculates pi, the compiler will probably just inline it.
Exactly, yeah.
I mean, if you write like incredibly stupid code like that, the compiler is just going to say, yeah, you can just use constant.
It's true, but let's not write stupid code, right?
Yeah.
So, so yeah, so you want to probably just, you know, kind of keep your code as compact as possible. Hey, speaking about code, I know this is a little bit off topic, and some of you are great coders out there. So question for you. So we're working on a game together. You guys are all part of the same team. Should I optimize as I go? What do you think? Why say no?
Because if you don't have a performance problem, right, and your game is running just fine, and then you start saying, oh, we need to optimize, and you take this perfectly readable and understandable code and rewrite it in a way that's more performant but less understandable and less maintainable, and you're essentially, you know, you didn't have a performance problem, you just solved a problem you didn't have, and now you've created a new problem with it. You've made the code harder to work with.
So wait, so is the short answer no?
The short
All right.
answer is
Okay.
optimize near the end if you realize you're having a performance problem.
Totally agree. And
Unless, but make sure at the beginning that your architecture allows you to, you know, optimize. Don't design things in such a way that it's impossible to optimize later.
I agree with that as well. So you may disagree. You might say, well, like, you know, when I write a story, I kind of edit the story as I go. But I'll tell you, I know a lot of writers, and they don't do that. They really write as quickly as possible, get through those chapters, kind of create the story arc, you know, all that kind of stuff as much as possible, outline everything, make sure it goes, right? It makes sense. And then go back and edit and add and interpolate and all that kind of stuff. And that's why I recommend as well, I recommend that you, when you're doing this stuff, you know, do it as short and sweet as possible. Other tools you might need in this course, which I'm going to talk about for a second, and we'll talk about it later on as well, is a tool called Desmos. And I think I'll put the link up on, see if I can go here, courses. So Desmos, I highly recommend for graphing, right? It's an online tool that's free, right? And if I wanted to graph something like the little formula that we saw here, like, you know, kind of A is equal to pi r squared. So I want you to assume when you use Desmos that we always have a y. So y is equal to whatever I put here. You know, so pi r squared. So if I type in, you know, pi, I just typed in pi, right? And then if I go r, you know, to the power, I can use a caret. So above the 6, you know, power of 2, right, kind of thing. I can add a slider for radius, right? Here's the radius. And really, if I say that x is equal to pi r squared, right? Or y is equal to pi r squared, let's just say that. You can actually start calculating stuff, you know, kind of right away. where you can see a circle being kind of emitted from the very first time, right? You're going to have to do some graphing in this course. Right? What's that? See you later.
Not my day.
Right. Wow, that's a long time to figure out it's the wrong class. Right? Wait. Am I really game dev? She liked it. I don't know about that, but I know, like, damn, I'm talking about physics and calculus. And wait, am I in the right class? I don't know what she was doing. But anyways, who knows? All the power to her. So yeah, so you can use. Please take note of this tool. I will be asking you to graph some stuff today. We'll be talking about in lab. I'll try and graph things by hand, and there'll be other opportunities for us to graph things for your assignment. So please take note of this tool. I'll ask you to do screenshots. A lot of times I want to graph because I want to visualize what the heck I'm trying to do, right? So Desmos, free tool, highly recommend. Okay, so that's pi r squared. And again, I want to find the circumference of a circle. I can calculate that by 2 times pi times r, radius of the circle, and whatever that is. Notice when we went to Desmos, it asked me to do a slider. So I can increase or decrease the radius and to see the effect immediately, right? So if I want to make a larger circle with a greater radius, I can do that, right? And the great thing is with Desmos is you can add as many of these kind of formulas as you want, right? So if I say, like, you know, if y is equal to pi r squared, and if I say that, you know, if you think about the formula, it'd be like f of x, so the function f of x is equal to x plus something. So if I say, like, you know, x plus 2, right? And if I add a slider for x, whatever x is, then I can calculate x plus 2, which is kind of a linear curve. There's no curve here. I can also do some other stuff, and you can kind of overlay all this stuff all together. So if I go to another f of x, right? And if I calculate things like, you know, cos x, right? You can see that I can get a nice little wave in there and all that kind of stuff. It can calculate things for you, and it can somehow simplify your life if you understand how to graph your functions. All right, so it's identity, kind of how to figure out the circumference of a circle. We need to find the circumference of a circle sometimes because we want to calculate the size of your bounding box. Sometimes I say bounding box, I'm saying circle, because sometimes circles make more sense than squares, right? Or cubes. Why is that? Because of a problem that that you have when you have a 2D shape, as an example. Let's go to 2D, but it's irregularly shaped, and you have this big space. Okay, so let's just go in here for a second, and I'll use. Hopefully, I have some stuff here I can show you. Here we go. So let's suppose you have some assets, and I'll have a little plane asset for you or something else. Let's try this plane over here. This is a classic, right? So plane 1, plane. So here's a classic. I'm just using Fireworks. That's one of my favorite programs. Nice and simple to use. It's a kind of a reduced function set from Photoshop, easier to learn. So I've got my little plane here. And notice that when I zoom in, you can see that there's a bounding box immediately. When we draw stuff with our tools, you see that there's always going to be a bounding box. What's a bad thing about this bounding box, though? Well, this part, right? This part right here. If I'm going to collide with the bottom part of my bounding box, right, I may have a logical collision, which we're going to be talking about later on in this course, but I'll have no visual collision, which is very bad for gameplay and user experience, right? So you sit there and you go, wait, I should be colliding, right? You know, or I shouldn't be colliding, and I'm not. And here's another thing. Notice that my this bounding box also includes the shadow. Should I care? I'm colliding with the plane shadow. In 2D, probably not, right? And I can reduce the size of my bounding box, right, when in calculations to make it kind of, kind of a little bit smaller, so a little bit more efficient, so that there's less dead space like this, right? But remember, I can use any kind of shape I want to kind of bound my object, right? So if I go and do things like an ellipse, let's see if I can do this. Of course, I'm always bad because I'm in real time here. So here's my circle. Let's see if I can make this more of an ellipse. I can also use ellipses for that. Let me just take that away and add in a border. Let's make that border a little bigger so you guys can see it. Share, there you go. All right, so, I mean, it's not perfect, right? Ooh, whoa, what the heck? That is not what I wanted. Yeah, so what you have is this border, and one thing to note is when you have this border, you're kind of trying to put your border or bounding box around an object. Now, this is a much better bounding area than this square. Still has problems, right? This part right here. I can put my whole hand in here, right? It's a bad thing. So when I try and collide, if I try and do overlap, we're talking about overlapping collisions. This should not be sufficient, right? But still better than the square in this particular case. Any other recommendations if you're going to do some kind of overlapping collisions? And again, we're kind of getting ahead of ourselves. We're going to be covering this in the second half, but anyone else would do something different. Come on, Gold Cobra Games. Tell me what you're going to do, what you did different. This is the guy from last semester. A polygon, so more than one bounding box. Okay, anyone else? Any other solutions? Yes.
Make a square bounding box that's smaller than the plane. Like you don't necessarily need to have collision on the wing, but you definitely, like I'd say, the biggest problem area is that you're in front of the tip of the plane,
yep.
Which is where collisions probably matter more than under the wing.
Right. So some really good practical solutions. You can move this around, obviously, to make it different. Some people suggested more than one bounding box. That's okay. And when you create your own colliders, I'm putting it in air quotes here, you can make as many shapes, you can use as many primitives as you want, to kind of calculate, if it's a collision. But the thing is, the more of these primitive shapes you use, more calculations per frame, right? So you have to kind of optimize. And for 2D games that are really, really fast running, depending on where the collision is going to come from, that's where you want to put your collision detection. All right, so that's primitive shapes in a nutshell. And again, sometimes I want to calculate the radius. Now, this is a radius of an ellipse, which changes. You'll have two, kind of center points for the ellipse, one on one side of the circle, one on the right side, one on the left side. And you can even have one in the middle, 3, to kind of calculate where, what the radius is across different points. But the basic thing we're using before is this idea of, the circumference is 2 pi r to find out, kind of the distance. All right, we talked about radians and all that kind of stuff. Usually we have 360 degrees in a circle. Well, we also say we have 2 pi radians, right? 2 pi radians. We need to convert them like we talked about before. I'm not going to cover that again. So again, 1 pi radian is 180, or 1 pi, full pi is 180 degrees. So 2 pi is a whole circle, 360 degrees. These things are typical. And here's some calculations to convert back. So 1 degree is equal to pi over 180. So you can literally convert that, but why would I do that when there might be just a number to multiply by, again, to convert back from or to radians or degrees. All right, so simple stuff. Any questions so far? And again, I don't want to go too fast, but I mean, some of this stuff should be review for you, right? It shouldn't be something new. Anyone not ever do trig in high school? How about functions? You didn't do trig? Okay, how about functions? Do you guys ever anyone not do functions in high school? Whew, thank God, right? Not knowing how to do functions and doing this stuff, especially programming, is like, right? It's crazy. But trig, yeah, if you haven't done trig in high school, how about calculus? Anyone not do calculus in high school? Okay, so for those people who didn't do calculus, it'll be a little bit more challenging when we get to derivatives and integrals. If you've done calculus, this will be a nice, easy review. Triangles. Okay, so let's talk about naming triangles here. We have, triangle ABC. You're always going to hear about this. Triangle ABC, and you have an angle. Where do I put how do I calculate when I say ABC, those are the 3 vertices of a triangle, right? And the way I talk about the triangle is typically how I draw it. Now here, if it's ABC, right, I should really draw the B on the left side, right? Because it's natural to go from left to right. So it's a A on the top, B on the left, C on the right. Here, this triangle really should be ACB, right? The way I look at it, right? Because it's kind of going to the left. That's the way I look at things. Everyone has a different way of noting it. And if you were to draw it the other way on a test or something like that, it'd be the same, right? It doesn't matter which way you flip the triangle. As long as you have the same angles and distances, you should get the same results. Also to note that there are not just capital A, B, and C, but also small a, small b, and small c. And those really, are for the distances between, let's say, the capital A and the capital B. So the distance between capital A and capital B would be C. That's the length of that line, line segment. The distance between capital B and capital C is alpha. All right, I'm going to use alpha, maybe, I should say A, B, and C, small a, small b, small c. And there's also inside, there's other little symbols, alpha, beta, and gamma, right? Which are Greek symbols for the angles, right? So if I want to find the angle alpha near vertex A, capital A, right? And as long as I have two other lengths of sides, if I have C and B, lower c, lower b, I should be able to calculate it using trigonometric identities and or Pythagorean theorem. Okay. Here's something. Can I use Pythagorean theorem here? How could I, for people who know Pythagorean theorem, how could I use Pythagorean theorem here? What would be a way of doing that? Yeah.
You can slice the triangle up into right angles.
That's right. So I can make a line, right? Kind of a line that goes from capital A all the way down straight. If I was to actually draw this with a ruler, all the way down to this line CB, as an example, straight down. And if I made this into a right angle, I'd have two triangles, AC something else, let's call it P, ACP, and APB, right? And if I had those two triangles, then I have two right angle triangles. And then from there, I could figure out more information about my triangle. However, one thing I don't know is this. I don't know this side at all. And so when I split this down the middle, I don't know how much of A, lower a, is on the left and how much of lowercase a is on the right. I don't know how much of that distance I'm splitting, right? And that's another problem. I may know also this distance also. It'd be nice to know the distance between this vertex and the line to make a perpendicular kind of triangle, right? It'd be nice to know those things. But again, you can kind of figure that out as well. We'll talk about that in a second. So again, simple triangles. We talked about all triangles, all interior angles add up to 180 degrees, right? This is important to understand. And that means that if given a certain angle, if for example, angle A, lowercase a, is 60, then the other two angles must equate to 120 degrees, right? 60 plus 120 is equal to 180. Again, please forgive me if I'm going too slow for you and I'm boring the crap out of you, but I got to cover this stuff for people who don't know. And besides, this will fill in some of the holes for people who forgot. All right, so here's the case here. What do we know about these three triangles, right? Well, we know that each triangle adds up to 180 degrees, right? But what do we know about this angle here and this angle up here? Is there any kind of identity? Do we know anything about this, the way these things have been drawn? Assuming that these two lines here, this line and this line, are parallel. If you assume those things, then what can we tell about this angle and this angle? Anyone know? They're the same angle, right? That's why they're labeled the same, right? Same thing with this angle down here. This is going to help you guys when it comes to physics, right? Because if I might ask you, for example, the declination or the depression, right? This angle could be called a depression, right? If you look at this as the top, right? So I kind of go down here, and this would be an inclination, right? If I kind of come this way, right? Well, this angle and this angle are the same. So if I want to calculate something, which I'll do later on in lab today, right, and this week, then I can just assume that this angle and this angle are the same. And this angle and this angle are the same. And you can see that they're all mapped out the same. This is an interesting picture. I recommend if you're going to make your own cheat sheet, which I might allow you to do for test number 1, you might want to include this picture to remind you that this is the way things work. I'm also going to probably give you a cheat sheet in advance, speaking of cheat sheets for the test, right, of my own. I'll say, hey, look, here's a cheat sheet that I made. Add to it, right? Add whatever you want. Which is kind of cool. It means you can add formula, you can add, kind of examples to help you out on your tests, whatever. It doesn't matter to me. At the end of the day, you're only going to have a limited amount of time. So chances are when a professor gives you a cheat sheet, it's not a good thing. It means that you don't need to know the formulas. but I'll allow you to customize it your own way. When you do your cheat sheets, I'm not going to allow you to print them out with Photoshop at 2 point, all right, like 2 pixels. I don't want you to come in with a magnifying glass, okay? Please don't do that. And I had a student one year, they made a cheat sheet and they made it in 3 colors, right? And they brought, I'm not joking around, they brought glasses that could see in red, green, and blue, and they wrote over top of it with red, green, and blue. Yeah, it's pretty crazy. So he had really 3 cheat sheets, right?
But he wrote it by hand.
He wrote it by hand with red, green, and blue.
Is that still allowed?
No, it's not allowed. Please don't do red, green, and blue, right? Please write legibly. Please don't try it. Writing it by hand is okay, but I mean, I'd be impressed by it because, you know, he's pretty much a real geek to do that, right?
If we manage to write it.
Oh, God.
If
All
we
right.
manage to write it small enough, is anything we write by hand is fair game?
Anything you write by hand is fair game, but I may not allow both sides. I may only allow one side. It's the cheat sheet. So whatever you can fill out. A lot of times it distracts you, though, to be honest with you. Like imagine if they bring in a micro, you know, kind of a magnifying glass to kind of look at something really, really small on the cheat sheet.
But with typed.
Typed is bad, right? So don't do type. That's why I don't allow typing or any kind of, if you're using Illustrator or Photoshop to create your cheat sheet would be bad. Okay, different kinds of triangles here, right? We have one triangle with all the sides the same, right? An equilateral triangle, right? Then you have one with 2 sides the same and one with 3 sides completely different, right? All sides are different, you know, kind of lengths, right? So 3 types of triangles. Okay, so one is an equilateral triangle, an isosceles triangle, and a scalene. Scalene would be the 3rd one on the right. Again, this is just nomenclature, right? So just talking about when I say you have an equilateral triangle, what does that mean, right? Okay, there's a couple of 2 things. There's 2 legs and a hypotenuse. When you talk about a right angle triangle, hypotenuse is really, really important because we use it for trigonometric identities, right? And it's usually the angle that's, the side that is opposite the right angle, right? So you have your right angle, and across from it on a diagonal is your hypotenuse. So going back, when we talk about right angles, here it is. You can see that the right angles are usually denoted by this square. So whenever you have this square in your calculations, for those people who didn't take trig, that means it's a right angle, right? And you can see that there's a little arc that goes like this. This little arc denotes less than a right angle, right? So, okay, so I have a right angle, and I have these 2 things. This is 90 degrees. That means these 2, alpha and beta, must equate to 90 degrees to make the whole 180 degrees. Again, basic logic, but we're going over it again. If I wanted to find this angle alpha, right, and I know the hypotenuse, and I know this one, which is the adjacent angle, or the nearest neighbor, if you will, right? So this is called adjacent. This is called hypotenuse, if I'm looking at angle alpha. And this one is called opposite, right? So opposite over hypotenuse, opposite over adjacent. Sometimes we have that, and we're going to talk about SOHCAHTOA. You guys should know that. That's like a standard thing to calculate angles when it comes to, you know, figuring out the angle of angle alpha or beta. Again, if I was going to look at angle beta, then this little a would be the adjacent, right? This is the hypotenuse, and this would be the opposite, right? Because it kind of, it's almost like the middle of this. If you can draw a line, an imaginary line from the angle here to the opposite side, then this would be the opposite, this would be the adjacent, this would be the hypotenuse. Okay, I'm just talking about it so you guys, you know, have that in your mind when it comes to calculating stuff. Questions so far? I know it's not the most exciting things, guys. And I apologize on a Tuesday morning after a long break, 8 o'clock in the morning, to come together and talk about right triangles. I'm sure it's not the most important or even the most interesting thing. All right, so we have this this old Greek guy, Pythagoras, right? Back in something like 494 or 569 to 494 BC. He lived quite a long time. And, you know, for that time anyway. He was really cool because he kind of calculated, you know, the idea if I have a right angle, I can calculate the, you know, and kind of the distances of 2 sides, I can calculate the other side, right? The opposite angle, if you will, which is kind of cool. And he developed algebra, him and this other guy, René Descartes, right? He's the one that kind of created algebra when it came to combining his theories with Pythagoras, right? So modern algebra has evolved ever since then. It's kind of, come a long way, but you can see that exactly what we talked about before. We want to make a perpendicular line that splits two triangles, right? And now we have two triangles that are right angled. And from there, if I know the length of the perpendicular line, I can pretty much figure out the length of the other sides, right? Like this side right here. Again, we do need, as a dependency, a right angled triangle to use Pythagorean theorem. All right, so Pythagorean theorem says that, the length of one side is equal to the square root of the powers, the squares of the other two sides, right? And when you look at this equation, like we talked about, square root of anything in every frame. So if you're thinking about a game that runs, 60 frames per second, right? And how fast is a frame? If I say 60 frames per second, how many milliseconds is a frame? Don't answer, because you always answer everything. Anyone else? I'm going to pick on somebody up here on the right corner. Jet, I know, I'm looking at you, man. No, not you. Jet, tell me what see, I know. I'm going to pick random people. I'm going to go over here. Okay, what about the lady in the middle? Tell me.
Sorry.
Yeah. So square root, how many milliseconds are in every frame if I'm running at 60 frames per second?
I'm sorry, I'm so sick right now.
I'm sick too, man. I'm sick, right? I just came from Colombia. I'm pretty sick. Go. Yeah. 16.66. That's what you're going to answer, right?
I was saying about 16, yeah. 16 and like
16.6666, non-terminating repeating forever is roughly the amount of milliseconds that we run every frame. Was that?
If you're saying it.
Yes. That's exactly. And if you think about that, if it's 16.666 non-terminating repeating forever and ever, first computer's going to stop at some point because they can't calculate forever, right? Most computers. You get to figure that if I do this thing every 60 milliseconds, right? So 60 times every second, I'm calculating square root. And square root is a heavy-duty calculation. And I'm trying to figure out the distance. And I have, for one enemy and one player, computers can handle that kind of calculation. What about for one player and a particle system of enemies, right? Like 10,000 enemies. Yeah, that would be really bad, right? Calculating distances between the enemies over and over again for one player, that would be really, really bad. And this is why we have different forms of collision where we don't use this formula. Yes?
Yeah, I was just going to say, because that's the thing, right? The difference between just purely theoretical math and programming is you have to often remember, things which give the same result mathematically or approximate it might be much easier to perform, like a square root. Or like another example is multiplying by the inverse of a number is much easier than taking one and using the division.
I totally agree with you, and I don't want to cut you off, but you're probably losing most of the people 8 o'clock in this class who haven't had coffee. Yeah.
Just use something like approximate the square root or only check for division.
Okay, I like that. That's another method. Approximating square root is not bad. What about not square rooting at all, and squaring the c? Right? That's faster. Why is that? No square root, right? So if I was going to do a squared distance as opposed to a distance, so two different functions, right? Squared distance and distance. They do the same thing. Why? If I know c, if I want to calculate c, and if I don't square root it, I'm going to get c squared, right? A squared plus b squared is equal to c squared. That's really Pythagorean theorem, right? So that means I get a squared distance. And if my collision checking algorithm doesn't care, as long as it has a number to deal with, if I say that if the distance is less than c squared, as an example, between the two center points of a circle, then I have a collision. It doesn't matter whether you do that or c is equal to the square root. So there's different ways to do that, and that's the one way to do it. But we talked about other ways as well. All right, so you got your right angles. Okay, this is interesting. There's something called these magic triangles, and you're going to run into them. And it's good to know that there are magic triangles. So 3, 4, 5 triangle. This is a standard pattern. So if I didn't have the 5 in here, right, and if I was going to try and calculate this distance with Pythagorean theorem, if I said a squared plus b squared is equal to c squared, you get a 5 if you have 3, 4, and 5. Exactly 5, right? What's other ones? Does anyone know any other magic triangles like this that you should remember? 1, 2, root 3 is one of them. right? 1 root 2 is another one, right? And you guys should know some of these things, that they're magic triangles in that they are always going to equate to that over and over again. And why would that help? Because on a test, it'll speed things up for you, Matt. Right? That's why. You'll look at it and go, wait, Tom gave me a 3, 4. Oh, wait, that's a 5. I don't have to calculate Pythagorean theorem. I don't have to use that. I know that if I have a right angle and if I have 3 and 4, the other side is 5. And here are some example of Pythagorean triples: 3, 4, 5, 5, 12, 13, 7, 24, 25. I'm not going to get you to memorize any of these, right? But it'd be nice to know some of the smaller ones, right? So take a look at some of those. There, if you look at Wikipedia, there's a lot of them that are very common. But 1, 2, root 3 definitely for sure is 1, 1, 1, root 2, and 3, 4, 5. Those are the very common ones. Yes.
Do we get a break in this class?
You want a break? It's 9
A
o'clock.
break, because I just need to walk around, or else I'm
You're going to fall down?
pretty much.
I'm sorry.
It's
Yeah.
not your fault. It's my own fault.
Maybe it's my fault because I'm boring the crap out of you guys. But I'm trying my best, right? I know it's the driest material ever. Well, if you want to take a break, go.
Yeah.
I want to power through because there might be questions afterwards, and don't worry, I'm recording it anyway. Okay. You guys are gonna both go for a smoke, yeah? Okay. So again, here's some examples, some 2 common triangles: 1, 1, root 2, and 1, 2, root 3. Notice there's also common angles that go along with these triangles. Okay. So a good example is whenever I have 1, 1, root 2, chances are there's 2 45 degrees. It has to be actually 2 45-degree angles and a right angle, which means this is an isosceles triangle, right? Because these two are the exact same side, and this is a different side, right? So isosceles triangle. Here we have a scalene triangle, 1, 2, root 3, right? Where you have 60 degrees and 30 degrees on this side. If I ever give you 60, 30, and 90, then you know the proportions are going to be in some scalar of 1, 2, root 3. They must be, right? That is the proportions of a triangle with 30, 60, 90, right? If I give you 2 45s and a 90, you know the proportions are going to be 1, 1, and some factor of root 2. You know it's going to happen, right? Questions around magic triangles. They're really, really important, especially when it comes to programming, right? Because you can predetermine the outcome by knowing these things exist. All right. We only have a few more slides to go, guys. Remember, the last part of all my PowerPoints are going to have example questions that I'm going to cover for you in lab, all right? Last 6 or so slides, right? So I'm going to go through the labs, and we'll try some stuff out for those people that forgot. And it'll be good practice for you guys and stuff for your assignments. Oh, one thing I will do in lab, once I get marked up with ACT class, I'll be using ACT class in lab. Typically not today. This will be the first day you're gonna get a break from ACT class, but every other time in lab, I'll put together this. You guys should know what ACT class is. It's a attendance registry that I'll be using, and I'm using it only because I know that if you're in lab, you practiced. Chances are, so if you come to me later on, you say, I don't get this, and I really did badly on my assignment, and I don't know what to do on my test. And if you never attended any labs, then I don't know what to do. I can't really help you too much. I can tell you to look at the videos, and we can sit down. But my timing is pretty tight, guys. So you need to book your time with me ahead of time. I'm not going to hang out and wait for you guys, to kind of say, Tom, I need you, kind of thing today. Can you book time with me today? No, you have to book it ahead of time. All right, so here's a triangle. We got ABC triangle, and it's sitting on X and Y axis. This is a very common scenario. Notice the X goes to the right, Y up. Again, please forgive me. You should know all this. And you have a coordinate, a point X, Y, where, or a vector X, Y, which is where you should look at this, right? And a vector has both, direction and magnitude, right? And I want to calculate X, Y, the distance. If I know A and B, I can use Pythagorean theorem to calculate my X and Y, right? And this is where we get into using, Pythagorean theorem to calculate distances, or the next step in a movement algorithm that you're going to make for your player. If he's moving diagonally, let's say, the next pixel, I want to calculate the next pixel of your frame, right? I want to be able to move my player in any direction, 360 degrees, right? And if I know where he was, and I know where the angle that he's moving in, I should be able to calculate the next pixel, based on my current position. Okay. Okay, so again, I've got two legs, and I've got some standard trigonometric functions. Sine, cosine, and tangent are the standards we use, and we can create other things like arctan, arcsine, and arccos, right? Also called cotangent, cosecant, thank you, and all the other ones. It's not really important because we can also say that sine to the -1 is the inverse sine. They also call different things. Or tan to the -1 is arccos, or that's another thing you can say, inverse tan, arctan. Thank you. And so on. You can do these things, and they all have to do with ratios of the other two sides, right? So what I'd like to do is, I'm going to kind of skip this through for a second. We'll go down to the next slide. I'm going to come back to the other one. Is you have this little equation, which I highly recommend. I'm going to put this on your cheat sheet, but you should remember this, right? And it really talks about the ratios of the other two sides. So if I want to figure out the angle, if I have the hypotenuse and I have this adjacent angle, right? So if I have A and I have H, and I want to find the angle X, then what I can do is I have A and H, and I want to find the angle X, so I'm going to use cosine, right? So cosine is kind of a quick way of doing it. I need the adjacent and a hypotenuse. But if I didn't have the adjacent and I had the opposite over hypotenuse, that would be sine, right? And so you can find out the different angles based on what the information we've been given. Again, in order for you to use these things, SOHCAHTOA, you need to have a right angle triangle, because it all comes back to Pythagorean theorem. These ratios of sides is what Pythagoras calculated way back, right? But it requires a right angle triangle. Right, so that's what this is really saying. So if I have a sine of x, as an example, let's go back to the the graphing algorithm. And by the way, with this thing, what you can do is I can delete some of these, so I don't care about this. And I do care about this. X is 1.2. Let's make x exactly equal to 1, right? And if I zoom in, you can see that when for cosine, let's go with sine first, because sine is kind of a more thing that we use all the time. There we go. So here's a sine graph. Okay, what do you guys notice about sine? If you didn't know sine at all, if you didn't know anything about it, and I said, find me the sine of a certain number, where x, as an example, is equal to some value, right? Like right now, x is equal to 1, right? So sine of 1, notice that as it rises, right, then at the top, right, pi over 2, right, as an example, or 1 is at the top. That's interesting, pi over 2. So that means this whole thing, this whole arc from the origin all the way to where it intersects with the x-axis, this whole arc here is pi, right? And knowing this, right, and if you look at this part of the your graph, you can see that when it comes to here, from the origin till it intersects again down here, right, as an example, right, that is pi, right? And if you go from here all the way down to here, that's another pi. So this whole thing here represents from the whole algorithm, the whole sinusoidal algorithm from here, this whole cycle, if you will, is equal to 2 pi, which means that's 360, it represents 360 degrees, right? I'm pointing this out because it's a lot of times easy to calculate some standard angles, right, or the standard results that you're going to get based on what you're looking at. So a good example of this is if I was to, let's get rid of this for a second, and let's put in here a sine of 30 degrees, right? Now this is interesting because if I put a standard angle, it just gives me the answer, right? So the answer is right here. If you look at Desmos, it gives me the answer right here. And if I add something, if I say, you know, plus 1, as an example, it'll give me the answer there as well. But if I put some random variable in here, like for example, you know, x, you know, it's squared, let's just try that. You can see that I get a really weird angle happening, where I'm calculating some, you know, some basic things. But you see the sinus graph, if you will, the sinusoidal graph, is the same interval after we get to a certain point. See this plus 1? Plus 1 actually shifts the graph to the right. Let's get rid of that. You can see now it's less of a shift, actually shifts it up, sorry. So why does this look like this? Does anyone have an idea why we have a graph that kind of bows in like this? Yes?
Because x squared can't be the first part.
Right? So if I have a number like, if x is 1, right, then it's a sine of 1, and that's the point they're going to talk about. If x is 0.5, the sine of 0.5 is going to be something less than 1, something over here, right?
X squared can be negative. X is imaginary.
Correct. The results you're talking about.
Yeah.
Don't confuse me, all right? Yes, you're right. You can have an imaginary number, and you can do it that way too, but we don't want to talk about imaginary W values. Thank you very much, okay? Not right now, let's go. But anyways, you can see that you can graph whatever you like, but the sinus algorithm, right, as soon as it passes this point right here, this first loop, if you will, is very regular, right? It keeps on kind of being basically regular throughout the entire time. Except if you notice something, it becomes tighter and tighter until the frequency is changed. And this is because we have a exponential value. It's rising in terms of complexity, if you will, for this particular calculation, exponentially, right? Because we've got that x squared value. Okay, you can also, in here, put another value. We can say something x plus 1. Put this value together. And you can see that if I did this, I'm going to go back to the origin for a second. You can see that it's a little wider. If I increase that to x plus 2, right? Again, it shifts things to the right a little bit more. And if I also subtract, so this is x, this is standard, right? And if I go plus, you know, 0.5, I can do that. You can see it'll shift one way or the other by 0.5, by the value of that I put in there. So if I want to put some x plus z, where I want to create a slider for z, right? So whatever that is, you can see that as I move the value up, it seems to slide to the left, right? And as I put the value down, it seems to slide to the right, right? Okay, so again, I'm just making you a note. I'm trying to get you to visualize sine, okay? But the standard sine, if I made this as, you know, kind of 0, so let's go back to 0 for a second. You can see that when the sine starts at the origin, moves up to the right, right? And then it kind of dips down to the right, and then that whole sinusoidal frequency here from here to here, this one loop or one hertz, if you will, from here to here, one cycle. Okay, it starts at the origin. Whereas for cosine doesn't start at the origin. One thing to note from I think it looks like this. Cosine starts not at the origin, but one up from the origin typically. So here, if you notice that this would be 0. Here, at this point, it would be pi over 2. At this point here, it would be pi. At this point here, it would be 3 pi over 2. And here is the completed cycle of 2 pi. So it starts off up. And why is this important to know? Because instead of trying to figure out things with your calculator again, you know that if I give you a value, as an example, in pi's, right, pi radians, you can figure out what the value is going to be. Okay, so if I say a cosine of, you know, as an example, pi over 2, what's the answer for y? If y is equal to cosine of pi over 2, then x is equal to 0, right? Because when in the origin where y is equal to y is equal to 0, then x is equal to 1. And when y is equal to 0, sorry, when y is equal to 0, x is equal to 1. When y is equal to some positive value, pi over 2, then x is equal to 0. all right? Actually, it's the other way around. When y is equal to 0, then x is equal to pi over 2 in this particular case, as long as it approaches this way. And so on. You can see that y is going to equal to 0 a bunch of times. It's going to start off positive. It's going to go to 0. It's going to go negative, and it's going to go back to 0. And it's going to keep doing that over and over again, cycling one way over the other. This is a great way of creating things like enemy firing patterns, right? Or enemy movement patterns in a sinusoidal wave as they come at you. Almost like a snake-like pattern. And if you combine some of these shapes, you can literally create different patterns when it comes to how enemies move around to kind of create a faux AI situation. What I mean by that is you can start your enemy somewhere here, you can move down to avoid you, come back, and you can kind of skip in and out to try and avoid your fire. Okay, I know it's not the most interesting stuff, but again, understanding how to graph trigonometric functions. Oh, one more thing we didn't do is tan. So let's go tan. Tan is a funny one. This is what tan looks like, right? So tangent, right? And it looks funny because of the way, tan is calculated. So tan is what? How do I calculate tan in terms of sine and cos? Don't answer all the time. I got to give somebody else a chance. If no one else asks, I'll come back to you. Yes. Okay. What's the other way? So how do I, when in terms of sine and cosine though, if I say tan is something sine and cosine, how do I figure it out? Sine over cos, right? So if you think about sine over cos, but you're not wrong. If you think sine over cos, it creates tan, right? So this tangent pattern. And if you notice, when we graph it, it repeats, but they're non-terminating repeating, right? So as you can see, they're asymptotic, right? So they'll go on forever, right? And the one thing there is there's no continuity between each of the lines. They'll never cross each other, right? No matter how far up you go, right? So if I keep on zooming out, they'll get very close, right? And you can't see this from a grid pattern perspective, but actually they never cross, right? And that's kind of a weird, a weird kind of property of tangent, right? They create this little pattern shape, but they never cross. What about if I wanted to flip this? I want it to go the other way. Is there a way of doing that? How do I graph that? So I want my enemy patterns not just to go like this, but I want them to go this way as well, right? Depending on where my player is firing their bullets. How do I make it so it goes the other way? Anyone have an idea?
1 over.
Okay, let's see if I can do that. So if I said 1 over, so if I go 1 over 1 divided by, sorry, I gotta remember how this works. You have to remove this and put tan of x, right? And plus z, there we go. So now it goes the other way, okay? And to see that together, I can add another one in there. Let's add another one. Let's see both of them together, right? So I can do kind of like tan of x plus z. And you can see that they cross over. You can make as many of these graphs, this is a really cool thing about this program, as possible. So I have 2 enemy movement patterns, to the right or to the left, right, using tangent. And if I follow that pattern, I can actually avoid things like bullets, creating almost like one part of the behavior of AI. Very simple AI, by the way, right? So it just avoids to the right or avoids to the left, right? Okay. We're almost done, I promise. Okay. All right, so we talked about this. So this is some trigonometric identities. Again, I'll put these up on your cheat sheet. You don't have to remember them. But these are some really important things. You know that sine squared x plus cos squared x is always going to be equal to 1, right? Okay, so that also that sine squared x from a notation perspective is also shorthand for sine x squared, right? It means the same thing, right? So if you see sine squared x, it equals to sine x squared, right? So that's an identity. And sometimes we have that. We have sine and cosine, and we have some other value, and we can figure things out by moving things across the equal sign. The other thing is that some other things, sine of x plus y is equal to sine of x times cos of y plus cos of x times sine of y, and the opposite one for cosine. Some basic things, I'm not going to go over each one of them, but these basically are identities, which means that if I sub these in, if I want to calculate something and I have some values, sometimes looking at the identities can help us solve the problem. Okay. Again, from a computer's perspective, again, I would have functions that do this for me. So I plug in parameters and then they spit out the value. That's what I would probably do. Okay. And I kind of covered this. This is a really important one as well. So this is the ratio of sides, right? So I have a side alpha, side beta, side A, B, and C. And I have alpha, beta, and gamma angles, right? As long as I know two of them, right, I can really, define the other side, right? So I have some partial information, I can derive the other part. And we're going to kind of try and practice that today in lab, right? So how do I use these things? Because it's the ratio of sides and angles that allow me to calculate the other information. Okay, and here's something else. So notice that it says that the Pythagorean theorem has another piece to it, right? So one piece that's missing is also this other angle. If you had some angle information, you can subtract it, and what it would do is equal to a squared. So this is another way of doing it where you don't have a square root. Here's another example, right? So I'm not using a square root to figure out a necessarily. I mean, I will figure out a squared, right? But I can use an angle, and I can use, as an example, this cosine rule, as opposed to when I don't have a right angle triangle. Okay. A lot of times we may need to find the angle of a triangle, and we know that the area of a triangle is half base times height. So understanding that, if you know what the base is, and if you want to find the height, L, as an example in this particular case, you can use this formula to help you out, and we'll talk about that in lab as well. Okay, and I covered this already. So this is really all I wanted to cover today in terms of like high level, and this will be on your test, this stuff. So up to now, up to here, that's all you really need from a trig or geometry perspective for physics. Anything beyond this is out of scope. And there's lots more, obviously, than this, right? Lots more. But I'm going to be covering some of this stuff in class today. And the way I do it is I have some examples. So here's an example. I want you to graph this thing by hand. How would you plot the points? This is just an example of, a practice of how to draw, kind of a Cartesian graph. How do I do this? We're going to kind of handle this in class. But usually I have 5 or 6 examples that I go over in class that we physically do together to get you to practice the concepts that I talked about in lecture. All right? And then what will end up happening is, we'll go over that. Anything I cover in class will probably, like I said, be a, kind of fair game for when I put it on a test. And you're going to see some of this stuff. Will there be a lot of trig on your test? No, chances are not, right? Again, there might be some more algebra on the test. You might use trig to figure out physics, but I need to talk about it because if you don't have this, then the next section, not this module, but the next module, will be near on impossible to do. All right, you'll see that. Any questions about the stuff I covered or any concerns that you have? This is the first day, so this is the best time to cover it. If you want me to do something different, that kind of stuff. I know somebody asked for a break, but I mean, think about this now. I'm done. So it's 9:30, right? This is the best time for us to meet. I have half an hour with you before the next lab coming up. So that's usually why I stop at this point. Sometimes I can't. I won't have this kind of time because there's more lecture material. There's more complex stuff that I'm going to be covering. But today is an intro lecture, and I don't want to blast your brains too much, right? So I know. I'm sorry. I'm sorry about blasting your brains. Yeah. Was it?
It's not the case for every section.
It's not the case for every section. What do you mean?
And have a lab in 30 minutes.
No, but some people do. Yeah. So any questions for me that I can answer now? Any concerns? Yes, in the back. Oh, that's a very good question. So where is the Slack group? So here it is. That's my Slack group. Any other questions? All right, please, guys, join the Slack group. This is a great way of communicating and asking me questions, even when we're not together. I'm not going to have, I'm going to be at the college. One more second, and then I'll shut this down. I'm going to be at the college on Tuesdays, Wednesdays, and Fridays every week, right? So those are the times you can contact me. Yes.
Will you upload this?
Yes, I will upload the presentation when I cross-list all the courses. So there's only one course, right? Everyone there. Otherwise, guys, thank you so much. For those people who I have in lab in 30 minutes, I'll see you there. For the rest, I'll see you tomorrow and Friday. Those are the other two labs.
All right, baby.